Okay, let's look at the simple pendulum. A simple pendulum exhibits simple harmonic motion. Let us consider the mass m at the end of a string of length L. So the mass can be hanging freely. It has m, and if it's hanging freely, then we can say that there is a weight acting downwards, mg, due to acceleration of gravity, and there's a tension T. Now let's swing the mass from its equilibrium position to a new position here. We see that the weight is still acting vertically downwards, mg, and the tension points this way. There is now a restoring force, mg sine theta, which points now towards the equilibrium position. The angle theta comes from this angle here, which is our displacement angle. So when we release this mass, it's going to just swing through the equilibrium position along an arc of length s. Note that the length of the pendulum is L. Let's now look at the forces acting on the pendulum. So we have tension, which is T. The unit of force is newtons, of course. We have the weight mg, and we have restoring force. This is mg sine theta. It's called a restoring force because it always points in the direction towards the equilibrium position, so it's called a restoring force. By applying an equation of motion, which is Newton's second law, we see that the net force on the system is equal to the mass of the bob, or the mass at the end of the string, multiplied by the acceleration. So the net force along the direction of motion is equal to mg sine theta, and that should be equal to the mass multiplied by the acceleration along the direction of motion. We write our acceleration as equal to d squared s dt squared, where s is the position of the mass measured along the length of the arc. Now I put a negative sign in. The negative sign indicates that the restoring force points towards the equilibrium position and is opposite to the direction in which the bulb is moving. Now S is equal to L times theta, where S is the position. I've already mentioned that L is the length and theta is the angular position. So we can take the derivative of S the first time. So we have ds dt, that's equal to L d theta dt plus theta dl dt. But note that since the length does not change, this the length dl dt is equal to 0. So our first derivative is just L d theta dt. The second derivative, d squared s dt squared, is the same. We shall just write L d squared theta dt squared. So now let's replace our acceleration formula in our formula above with L d squared theta dt squared. So we can write minus mg sine theta to be equal to m times L d squared theta dt squared. Cancel your m's and you are left with minus g sine theta equals L d squared theta dt squared. Let's rewrite this in a different way. Let's bring the d squared theta dt squared to the left, so we can write d squared theta dt squared to be equal to minus g over L sine theta. The reason I want to write it this way is so that I can compare it to a previous formula that we had for the motion of a simple harmonic oscillator. Comparing d squared theta dt squared equals minus g over L sine theta to our previous formula for simple harmonic motion. We write that formula below. So that formula was d squared x dt squared equals minus k over m times x. So in that formula, we had minus k over m to be equal to omega squared. So we can do the same for our formula, where in our case here, for the simple pendulum, omega squared is equal to g over L. So the only difference between what we've written now and our formula for simple harmonic motion above is that our formula depends on the angle sine theta. But that is not what we want for simple harmonic motion. So what we can do is, since our pendulum is going to be in simple harmonic motion, we can take a small angle theta. So for small angles theta, we can see that sine theta is approximately equal to theta, and I'll write that here. That's for small angles. So this is called the small angle approximation, and this is what we do for simple harmonic motion. We assume that the angle theta is very small, and this is what allows us to do simple harmonic motion with our formula. It's an approximation which simplifies our calculation quite a bit. So for this small angle, we can rewrite our equation of motion for the simple pendulum. We'll write d squared theta dt squared to be equal to minus g. Well, we've already used a constant, so let me remove the g. So we'll write minus omega squared theta. Now you can see that this form is exactly like what we had for the motion of a particle in simple harmonic motion earlier. So again, the formula, the solution would be the same, of course, but let's look first at the angular frequency omega. Omega is equal to the square root of g over L. Note that the period t of oscillation is equal to 2 pi over omega. So if we write t now to be equal to 2 pi over omega, then we can then write 2 pi t equals 2 pi square root of L over g, where we've just flipped over g over L. So the period of oscillation is therefore equal to t equals 2 pi square root of L over g. So note that for long L's, the period increases, and for that is for a given acceleration g, the period will increase when you increase the length L. Or if you fix the length L, increasing g will decrease the period of oscillation. So that's a quick way to analyze that oscillation formula for a simple harmonic oscillator or for a simple pendulum. Let's look next at a physical pendulum. For a physical pendulum, let's consider a solid object which oscillates about an axis that does not pass through its center of mass. In this case, because the object cannot be approximated as a point mass, we cannot treat it as a simple pendulum. We have to treat it as what is called a physical pendulum. So we can consider a physical pendulum consisting of a distributed mass fixed at a certain pivot point as shown in the diagram. Okay, I will now draw a diagram of the physical pendulum, and I'll try to keep it simple. So let's consider a mass that is pivoted at a certain point O. The center of mass is somewhere here. Let's write that as Cm. If that mass is now swung like that, the center of mass is now going to be this way. So the broken line here will represent the equilibrium position. Let's say the distance from the pivot point to center of mass is d. When we are swinging the pendulum through an angle theta, and so this distance from the center of mass to the equilibrium line is d sine theta. So we now have our system in a way where it looks a lot like our simple pendulum. So let me write here, this is the pivot point. We can again apply the Newton's second law, which is our equation of motion, where the net force equals m times a. In this case, if we think of the physical pendulum as rotating about an axis through the pivot point, then we can use our formula for rotational motion. So the net torque in this case is equal to the rotational inertia multiplied by angular acceleration alpha. So this is the rotational analog of Newton's second law, F equals ma. Note that the torque is equal to rotational inertia multiplied by angular acceleration. And note that our angular acceleration is the change in angle, the squared theta dt squared. So we take the angle, the angular position, we take the derivative of that twice to get the angular acceleration alpha. So our equation of motion becomes minus mg times d sine theta equals d squared theta dt squared, and multiply that by the rotational inertia I. Again, the negative sign just indicates that the torque is a restoring force and it points towards the equilibrium position. We are again assuming that the angle theta is very small, so we are still using the small angle approximation. So we can now write minus mg times d times theta to be equal to I d squared theta dt squared. Now let's rewrite this by putting mg times d divided by the rotational inertia together. Let's put the parenthesis around that, and we multiply that by the angle theta and set that equal to d squared theta dt squared. So by looking at this, you can see that the angular frequency omega is equal to let's say angular frequency omega squared is equal to mgd divided by I. So we can write omega to be the square root of mgd divided by I. And the reason we do it this way is so that we can write it in a form which is identical to what we have for the motion of a particle in simple harmonic motion. So we can now write d squared theta dt squared to be equal to minus omega squared theta, and you can see that this is now in the same form as d squared x dt squared equals minus omega squared x. So by doing it this way, we can now get the same solution for both equations of motion. So now analyzing our oscillation period, we see that the period t again is equal to 2 pi over omega, and so we can write t equals 2 pi square root of I divided by mg times d, and this is the period of oscillation for a physical pendulum. Now let's do a quick example to see how this works. So small amplitude of motion just means that we are using the small angle approximation. And so if you look at a figure, this is a figure of a rod pivoted about a certain point, like that. So this is our pivot point. Pivot point is there, and that's a pivot line. The center of mass obviously should be somewhere here. So this is cm, center of mass. And here is the mass multiplied by gravity to represent the weight of the rod, and the length is L. So we want to find the period of oscillation if the amplitude of motion is small. Small amplitude of motion, as I mentioned, just implies small angle. So this means that we can use our formula T equals 2 pi square root of I divided by mgd. Notice that we don't have to do any extra derivation because we've already derived a formula for the period of oscillation of a physical pendulum. And when you have anything that is not a point mass, something like a rod like this, you just treat it as a physical pendulum. And so the things we need now are the mass m is told to us to be given, which is m, the mass is m. D is the distance already from equilibrium. We are given that, so we won't worry about that. And the next thing we need to find is the rotational inertia I. Rotational inertia is also called moment of inertia. So rotational inertia or moment of inertia. So for a rod pivoted about an axis through one end, the rotational inertia is given by 1/3 ml squared. We can derive this certainly, but we already know this, so I'll just quote it for you. So we can say that for a rod pivoted at one end. Rotational inertia is given by 1/3 ml squared, where L obviously is the length. So plugging this in, the period of oscillation can be written as 2 pi square root of I, which is 1/3 ml squared, and then we're going to divide that by the mass times gravity times d. Okay, so note that in this formula, the letter d is equal to L over 2 because the distance d goes from the pivot point to the center of mass, and since the rod has length L, then it follows that d is equal to L over 2. So now we can write the period of oscillation t to be equal to 2 pi square root of, and we have m L squared divided by 3 mg, and then d is L over 2, so we write that this way, and we can simplify this to now be equal to 2L divided by 3g. You first cancel out the masses and then bring the 2 up and cancel one of the L's, so the period of oscillation is t equals 2 pi square root of 2L over 3g. You can also have examples like this for a torsion pendulum. And for a torsion pendulum, you do the similar sort of example. So I'll leave this to you as an exercise. So I'll say, try this as an exercise. Okay, so let's stop here, and then we will look at forced oscillations and damped oscillations next.